this is going to do... I bet that just broke the recording. I thought maybe I'd resized the window and broken the recording, but the number is still red, so okay. What this does is give you the actual coordinates. Where it says 0 from center, there should be a semicolon in there. There should be a lot more semicolons in my script. It's telling you this is the row that goes through the center of your mirror. And at 0 distance from the center, it should be 0 forwards. That's always going to be there. Doesn't really need to be. I could change that. Hold on. In this case, I'm looking at a 5 centimeter diameter, 2-inch backyard cheapo telescope. Should probably put 10,000, made a respectable 4-inch telescope. Primary focal length 500 centimeters, fairly normal for a backyard telescope, I think. And a grid line interval of 5 millimeters. I've added the extra zeros to try to reduce the rounding errors that may occur otherwise. Also, it means you're not having to deal with so many negative exponents. 5 millimeter intervals should be easy enough to do whether you're working with card or even with 3 millimeter plywood. You can cut slots and make everything fit together. But if you're working with plywood, you might want to make the intervals bigger than this. And that's what happens when I edit code on the fly. Line 90, let's have a look. Change your numbers. I made it a 4-inch telescope. I've gone to 9 millimeter intervals so you can make it with 3 millimeter plywood. How's that? And yes, those extra semicolons did get rid of the excess spaces, so there's your first shape to cut. This is obviously only one side of it. You need to do this symmetrically, and you only need one of that, but you need 2 of each of the rest of them. My bad, you need 2 of that, but 4 of each of the rest of them. 2 with the slots in the back, 2 with the slots in the front, so you can fit them together in a 2D grid. That's very few rows, but it is rows. So we are going 9 millimeters from the center, and 9 millimeters out, you want to, the row that goes through the center. 9 millimeters out, 4 hundredths of a millimeter forwards, 40 microns forwards. Nobody's going to measure that. 18 millimeters out, 162 microns forwards, 1/6 of a millimeter. 27 millimeters out, 365 microns. This is 1/3 of a millimeter forward. 36 millimeters out, 2/3, most of 2/3 of a millimeter forward. 45 millimeters out, 1 millimeter forward. These are quite small numbers. Out here at the edge, we are already 45 millimeters from the center of the mirror. I'm not doing circular mirrors. I'm doing mirrors that look square from in front. I have a fruit bowl like that. It's just easier. Obviously, your central point on this one is the 4500, 101.25 from the top row. So the very centre of this arc is going to be 1 millimetre forwards. The next one is 1 millimetre. Next point, 9 millimetres off centre. 1 millimetre and 53 microns forwards. And then full 45 millimetres to the edge and 18 millimetres along the edge from the centre. You are 1 1/6 millimetres forwards. And so on. Try again with more curvature, huh? Shorter focal length. This one is a 200 millimetre, also known as 20 centimetre, also known as roughly 8-inch diameter. So pretty big, but only a 50 millimetre primary focal length. So crazy. This is a really deep dish. And 20 millimetres between grid lines. So 20 millimetres out, 2 millimetres forwards, 40 millimetres out, 8 millimetres forwards, 60 millimetres out, 18 millimetres forwards, 80 millimetres out, 32 millimetres forwards. And finally, 100 millimetres out, 50 millimetres forward. Then in the next row, which is 20 millimetres off centre, misses the centre by 20 millimetres. You've got 4, 10, 20, 34 and 52 millimetres forwards. Missing the centre by 40 millimetres on the way through. You go, obviously, 8 millimetres as you pass the centre, and then 10, 16, 26, 40 and 58. On your last row along the edge, the centre of it is going to be 50 millimetres forward, 5 centimetres, roughly 2 inches. And then you're going to be 52, 58, 68, 82 and 100 forwards. So this whole thing is 100 millimetres, 4 inches deep. 50 millimetre focal length. This doesn't quite sound right, you know. A 50 millimetre focal length on an 8-inch scope. Why am I mixing imperial and metric units? Oh well. It looked right when I did the dots. I've been working in millimetres when I've been talking here, but this is all unitless. The whole thing scales. You can call these hundredths of an inch or thousandths of an inch. You could call this 20 inches at the top, and a 5-inch primary focal length, a 2-inch grid line interval. You want to work in thousandth of an inch and build a 16-inch reflector. And put your light source 2 feet in front of it. And you're going to build the frame to support this out of card, so you can slot pieces in every 1/10 of an inch. That's your central card. Those are the coordinates for it. I'm sorry, this isn't quite as tidy as you might like. Also, 0.1 thousandths of an inch, 0.4 thousandths of an inch, 1, 1.7 thou, 2.6 thou, 3.8 thou, 5 thou. These are requiring some really fine cutting at these fine intervals. When you get out to 8 inches out, 666. I lived alone. Sorry. Thou, also known as 2/3 of an inch forward. If you're going to do things in this much detail, you probably want to remove one of the semicolons and make it, spread these vertically down the page. Then again, you only get, I think, 24 rows of text on the page, so it wouldn't fit if you did that. If I played through this whole thing, we could be here a long time. That's only a tenth of the way through. Anyway, there you go. The code will be in the description. And BeebEm can just be Googled and downloaded. It's free. You can now get coordinates for your own parabolic reflectors. So Rich, if you want to actually test the hypothesis I put forward as an explanation, let's say the explanation I gave you. Yeah, well, I just did the explanation I gave you. The reason the penumbra becomes that obvious more quickly has to do with the light source having a much larger angular size. Well, you can use this program to get these coordinates and build your own parabolic reflectors. They don't really have to be precise. It's just easier to get bright enough light to work with if you get one that's good enough. And then you can, repeat your penumbra size measurements with various size light sources at fixed distance. Remember, it's the mirror. Wait, it's the front edge of the mirror, not the light source, that you want at the fixed distance. And also with the same size light source at varying distances. 2 independent variables. And show your results. We're still only halfway, 4,000. It's 8,000 to the edge.